All right, guys, here we go. Verifying identities. Now, 5-2, we're going to start out with a big long list for strategies. These are things to keep in mind when we are verifying identities. And again, verifying identities is not solving. We aren't solving anything. We're not moving back and forth and finding a solution. We are saying this is how this identity works. This is how you can get the right side from the left side. You're going to use this type of thought process in calculus. You don't verify as much, but you're going to use the same tools when you're finding derivatives, when you're changing the form of integrals, and a lot of other skills that you're going to do in calculus. Hopefully you're noticing that the higher the level of math you go, the more conceptual it is. The more you are solving a problem, not memorizing a set of steps. You're finding connections, and you're finding the way the numbers work and the functions work together, and using that to get where you need to go. That's what we're learning with verifying identities. So for those of you who aren't moving forward into calculus, this is a job skill. Learning to find connections and creatively problem solve is definitely something that your employers are going to want to see you be able to do. Okay, one way to go. Learn those fundamental identities that we talked about in section 5.1. Get familiar enough with them so that whenever you see either side, you think about that other side, and be aware of equivalent forms of those fundamental identities. For example, this is just my main Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. This is just an alternate form. We used that in the notes for 5.1. Another way to approach things is to try to rewrite the more complicated side. Now, sometimes there isn't a more complicated side. Both the left and the right sides look rough. But if one side is simple and one side is complicated, try that. Start with a more complicated side. Number 3 says that it's sometimes helpful to express all trig functions in terms of sine and cosine. That's something else that we did in 5.1. We rewrote tangent and secant and cosecant in terms of just sine and cosine, and then we simplified. So that can be a really useful tool. Number 4 is a big one. Usually, any factoring or indicated algebraic operations should be performed. So if you can factor, or if you can do some algebraic operations, usually that is going to help you move forward. Here are some reminders about some algebraic identities that you should know from college algebra. If you don't remember these, you need to brush up on them. You need to know what squaring a binomial looks like into a perfect square trinomial. This is both squaring binomials. This is with a sum, this is with a difference. You should be familiar with difference of cubes and sum of cubes, what that pattern looks like. And you should be familiar with difference of squares. If you do not remember how to do these algebraic operations, I encourage you to go look up some Khan Academy videos. So here we're going to square binomials. And when I square binomials, I get perfect square trinomials. That's both of these. Then I've got sum and difference of cubes. That's these two. And then I've got difference of squares. So if you need to go look those up and do some practice, that's what you're looking at. For example, this is a perfect square trinomial. When I see this, it should clue you in that I can factor that out like a quadratic equation, use reverse FOIL, and I'm going to end up with a binomial square. If you want to see that off to the side, this is a perfect square trinomial, and it's going to give me a binomial squared. If I want to think about reverse FOIL, sine square x plus 2 sine x plus 1. If I want to look to see what factors that would be, I've got sine x times sine x gets me sine square x. 1 is prime. Both signs are positive, so both of these need to be positive. That is a repeated factor, sine x plus 1 squared. When you see this, and you should be able to identify perfect square trinomial, sum of squares. All right. Sum or difference of two trig expressions can be found in the same way as any other rational expression. For example, 1 plus sine theta, 1 over sine theta plus 1 over cosine theta. If I find a common denominator, it says to write with the LCD. Well, my LCD is going to be sine theta cosine theta. So for this expression, I need to multiply by 1 that looks like cosine theta over cosine theta. And for this expression, I need to multiply in the sine theta. So I can multiply anything times 1. 1 is just something over itself. And what I get from that is cosine theta plus sine theta as my numerator and a common denominator of cosine theta sine theta. Okay, that's how to use algebraic operations and factoring. A fifth way to try when I'm trying to verify identities is to be aware that as you select substitutions, keep in mind the side you're not changing. That's your goal. Always keep your goal in mind. For example, if I'm asked to verify this, I want to think of an identity that are going to tie these two sides together. Well, I've got tangent square x and I've got cosine square x. And you know what? I know that secant x is 1 over cosine x. And that I have a Pythagorean identity that says secant square x equals tangent square x plus 1. That's one of my Pythagorean identities. So that secant function is the best link between those two sides. And finally, my last tip and trick, my last tool that it gives you for 5-2, if an expression contains 1 plus sine x, sometimes it helps by multiplying the numerator and the denominator by the conjugate. Well, what's the conjugate of 1 plus sine x? Conjugate is the same two terms with a different algebraic sign in the middle. So the conjugate of 1 plus sine x is 1 minus sine x. That gives us 1 minus sine square x, because when I multiply two conjugates together, I get difference of squares. And that links to my Pythagorean identity. I can replace that with cosine square x. Similar procedures apply for all of those. Now, don't get overwhelmed right here. You are just now being introduced to 6 different ways to start and to try to approach verifying identities. This is why we do practice, so that you can start using these methods and getting more comfortable, so that when you come to them on your own, you'll be able to say, oh, that's what I want to do. And you have a starting place. And if your starting place doesn't work, you know to go back and try something else. One more time, the procedure for verifying identities is not the same as solving equations. Techniques used in solving equations, like adding the same term to both sides, multiplying each side by the same term, should not be used when working with identities. You're not, as a general rule, working back and forth. You are going to work only one side at a time. You are not moving things back and forth. You're focusing on working on one side. All right, verifying identities by working on one side. To avoid the temptation to use algebraic properties of equations to verify identities, one strategy is to work with only one side. Now, this doesn't always work. You can't always work down one side and make it match the other. A lot of the time it works. Sometimes you have to simplify one side till you get to a point where you're stuck. And then you go work on the other side to see if you can make it match. Just a reminder, don't drop the argument. Now, I'm going to give you one way at least to verify each of these identities. Keep in mind that there are multiple ways. Okay, so we're just going to work down one side. We're going to pick the more complex side and work on it. The more complex side is the left. So I'm going to work on the left side and try to see what I can do to it to make it match the right. Well, I don't see a tangent, but I can rewrite secant in terms of cosine. So let's do that. Let's write it as 1 over cosine theta times that binomial in parentheses, and then we're going to distribute and see what we get. When I distribute and I multiply them in, I get sine theta over cosine theta plus 1. Oh, look at that. And sine theta over cosine theta is tangent theta. And I'm done. I have verified the identity. Notice, I did not move anything back and forth. I just worked down one side. I used algebraic properties. I changed this into terms of sine and cosine. I simplified, and then I got the matching side. That identity is now verified. Do not skip steps. You have to show me how you get from here to there. You may be able to look at this and go, oh, if I turn that into 1 over cosine, I got tangent plus 1, and I'm done. But see, if you go straight to here, I don't know whether you really thought through that in your head or you're just giving it a go and hoping that I don't notice you didn't show me how to get there. So you've got to show me the steps. Okay, verify this next identity. Again, we're not saying, is it an identity? I'm saying it is an identity. You show me how. This time, the more complex side is my right side. So I'm going to work on it and try to make it match the left using that same process. I'm going to take cosecant theta and rewrite it as 1 over sine theta. Distribute. And then recognize that this is a quotient identity, cotangent theta plus 1, and that was my goal. That was what I was heading toward. Now those were very, very simple and basic. Not all of them, obviously, are going to be that simple and basic. Let's do some that are a little bit more complex. We're asked to verify working with one side still. I'm going to pick my more complex side. Now you have different ways to go. You can absolutely attack this by turning it into sines and cosines. That's not the way I'm going to do it because I'm going to choose to show you a little different. But if you want to change it to sine and cosine and do your own thing, that works because multiple approaches. I'm going to distribute. And then I'm going to use my quotient or my reciprocal identity here and say cotangent square x times 1 over cotangent square x because that's another way to write tangent square x. And then when I multiply these two together, that's just 1 because that's cotangent square x over cotangent square x. And this is one of my Pythagorean identities. 1 plus cotangent square x is cosecant square x. And I have verified that identity. Let's go again. Keep your goal in mind. I'm going to encourage you to work the left side because it's the more complex side. You're welcome to change to sine and cosine right now, or you can distribute that tangent square x. Since this is just tangent, I want to change this. Well, you know what? It's not going to make any difference which one I did. I'm going to go ahead and take the reciprocal of cotangent, though. I'm going to replace that with 1 over tangent square x. And tangent square x times 1 over tangent square x is just 1. So I've got tangent square x plus 1. And tangent square x plus 1 is secant square x. Secant square x. That's not what I've got over here, though. I've got 1 over 1 minus sine square x. So how can I get there? Well, secant's the reciprocal of cosine, so 1 over cosine square x. And my link between cosine square x and 1 minus sine square x is that Pythagorean identity. Pythagorean identity, sine square x plus cosine square x equals 1. So cosine square x is going to be 1 minus sine square x, according to that Pythagorean identity, and I have verified. You need to see that Pythagorean identity that I used, sine square x plus cosine square x equals 1. I've got cosine square x, so cosine square x is the same thing as 1 minus sine square x. There's my substitution. So I take that out and I put the other side in. All right, let's go again. Still working only one side. Now it starts getting a little trickier deciding which side is the more complex side. We're gonna go ahead and work the left again. I'm going to show you two different ways to do this. The first method that I'm going to show you, we're going to say, okay, tangent square t times 1 over secant square t. I'm going to pull it apart so that I can more simply switch it to sines and cosines, because see, I've just got cosine over here. So I'm going to say, okay, tangent square t is sine square t over cosine square t. And then I'm multiplying that times 1 over secant square t is just cosine square t. Well, cosine square t basically over 1, that is going to cancel. Those factors cancel out, and I'm left with sine square t. And using that main Pythagorean identity again, sine square t is 1 minus cosine square t, and that's difference of squares. Difference of squares factors out to give me conjugate pairs. And I have verified my identity because those sides match. I worked down the left side and made it match the right side. Keep your goal in mind as you work. So that's one method. Let's do a second method. We're still going to work down the left, but let's do it a different way. Find a different approach. The left side is tangent square t over secant square t. You know what? These two are tied together with a Pythagorean identity. Tangent square t is the same thing as secant square t minus 1. If you doubt me, pull out your identity sheet that you should have right next to you while you're working this. Tangent square t, if I'm solving for tangent square t, I subtract 1 from both sides. Okay, so secant square t minus 1 is my numerator over secant square t. I could see two different ways at least to go from here. I'm going to choose to split this apart into two separate terms. Again, you're just going to have to do some practice with this, play with some things until you start seeing pathways forward. This is like solving a puzzle, trying to find that next step. Anything over itself is 1 minus 1 over secant square t is cosine square t, and then I've got difference of squares again. Whatever you do, you have to show me your steps so that I can see the connections that you made. All right, so two different methods. You never have to show me more than one way. I show you more than one so that you can see different ways to follow the path. All right, verify the following equation is an identity. I'm verifying, I'm not solving. I'm picking a side and working down that side. I'm going to choose the left again. So many choices. You know what? I like this where I split it apart into two terms from one expression to two separate terms, two separate rational expressions. Let's split this apart into two separate rational expressions and see what we can do to that. I'm heading toward changing tangent and cotangent into terms of sine and cosine. I'm just going to do it my way. You're welcome to try it a different way and see how you do. I bet that we match by the end. Don't forget to keep the argument with the same thing that they use. They're using t here, so that's what I'm using. So in order to make it more simple, not have to flip and find reciprocals of this denominator, I'm just going to pull tangent t out front and do 1 time over sine t cosine t as my second factor. And then I'm going to rewrite it in terms of sine and cosine. Now, I have common factors that I can reduce. Sine t on the left, cosine t on the right. That leaves me with 1 over cosine square t minus 1 over sine square t. I need cosecant square t minus secant square t minus cosecant square t, and that's what I have. I just need to rewrite it. Secant square t minus cosecant square t, because those are both reciprocal functions. And we have verified. If you were in the classroom with me at this point, you would be putting up your alternate methods. I'm sorry you're not here to put up those alternate methods so you can see the different ways everyone's mind works. Your mind doesn't work the same as mine. I can almost guarantee it every time. So everybody sees this differently. All right. The tool that we're going to make use of on this page is multiplying by a well-chosen 1. Multiply by a well-chosen 1. Remember that 1 is anything over itself. We are going to multiply by a well-chosen 1. I am going to show you how to do each of these working down either side. Because if I look at these identities, I can't pick which side is more complex. They're both fairly complex. So we are going to work the left side and make it match the right. If you choose to do that, that's all you have to do. But I want you to be able to see that you could also have chosen the right side and worked down it to make it match the left. Again, you don't have to go both ways. You just have to show one approach. But I want you to see your options. Okay, so working the left. If I work down the left side and try to make it match the right, I'm working with secant x plus tangent x over sine x. The tactic I'm going to use is to multiply by a well-chosen 1. You wouldn't think to do this yet, but after this you will, because now you've seen it. All right, secant x plus tangent x, I'm going to use the conjugate. I'm going to introduce the conjugate of that so that I can come up with difference of squares, because this reminds me of my Pythagorean identity, but I need those terms, those trig functions, to be squared in order to use that identity. So I'm going to multiply this by a well-chosen 1, and my well-chosen 1 is secant x minus tangent x over itself. I chose that because it is the conjugate of secant x plus tangent x. I am multiplying by a well-chosen 1. I can multiply anything by 1. It doesn't change the value, but it does let me get to this difference of squares in my numerator. When I FOIL together that numerator, I get secant square x minus tangent square x. Now in my denominator, I've got sine x, and I'm not going to go ahead and multiply this in. I'm going to leave it for the minute and stop and see what I end up with. Well, look at your Pythagorean identities. Secant square x minus tangent square x is 1. Now in my denominator, a hint that I needed to leave this is because it is still there in my goal. Keep your eye on the prize. Keep looking at the goal. My goal is to get this denominator, secant x minus tangent x. That's it right there. Now I need cosecant x in my numerator. The way that happens is because that's the reciprocal of sine. So when I do that reciprocal function, that gives me cosecant x with a denominator of secant x minus tangent x, and I have verified. That's working down the left. Now let's do the same thing in practice by working down the right. You're still going to use a well-chosen 1. This time your well-chosen 1 is secant x plus tangent x over itself. Now let me say it just one more time. Don't do both sides for homework. We're doing both sides now so that you get lots of practice. I encourage you to pause the video, work through it, and then check to see if you did the same things I did. Keeping my eye on the goal, I don't distribute my numerator. I do FOIL the denominator so that that is just 1. Using my Pythagorean identity, that is equal to 1, so now I no longer have a denominator. I just got cosecant x times secant x plus tangent x, and cosecant is the reciprocal of sine. So I can rewrite that as secant x plus tangent x over sine x. And I have verified. So I verified that identity working from both sides. All right, this next one, same thing. I'm going to show you how to work the right, and I'm going to show you how to work the left so that you see both ways and so that you have more practice. We are still going to use multiplying by a well-chosen 1. So let's work the left. I encourage you to pause the video, work through, and then come back to see if your steps match mine, or, just make sure. I wish I was able to verify if you do something different, if it's right or wrong. That just stinks as far as online education. We're doing the best we can. One minus sine squared x ties to my we're headed to this, and I need cosine x in my denominator. You know what? 1 minus sine squared x, Pythagorean identity, that's the same thing as cosine squared x. Notice that I don't ask you to write your link. I should be able to see it, that you did that substitution according to that Pythagorean identity. Now I'm going to factor out this common factor. Cosine x and cosine squared x, one of those factors out. So I've got 1 plus sine x over cosine x, and I have verified. If I chose to work the right, you do not have to do both. You do one or the other. If I chose to work the right, I'm still going to multiply by a well-chosen 1. And my well-chosen 1 is going to be the conjugate over itself. And I'm going to stop and I'm going to say, okay, what is my goal? Well, my goal is to end up with 1 minus sine x in the denominator. So I need to cancel this out, so I get cosine squared x because of the Pythagorean identity. And then I simplify that common factor. And I have verified. Do the left or the right, do not need to do both. But the more practice you get now, the better off you are. Okay, example 5. Now, notice that our attack method has changed. We're going to work both sides. These sides are both extremely complex. It's really hard sometimes, well, beyond our capabilities right now with what we know, to get from one side to the other without just so many steps. So I'm going to work both sides. Now, working both sides doesn't mean I'm solving. I'm still not solving. But when both sides are complex, I am going to work each side independently, not moving back and forth. Work each side independently until I get to a common expression. I'm trying to simplify to a common place for the left and the right. Okay. And we're going to do this one a couple of different ways, I think. No, my other way is really long. We're just going to do it one way. Okay, so over here, I am going to, I'm going to take this and I'm going to rewrite this left side in terms of sine and cosine. I could multiply that by, maybe that's what I did on the back. I'm sorry, on the back I tried multiplying by the well-chosen 1. Instead of doing the well-chosen one, we're going to write it in terms of sine and cosine. So I've got cosine alpha over sine alpha minus 1 over sine alpha, and then in my denominator, cosine alpha over sine alpha plus 1 over sine alpha. And notice that my numerator and denominator both have the same common denominator there. So I'm going to have cosine alpha minus 1 over sine alpha. Oh, you know what? I don't want to go that way. I want to multiply everything by sine alpha. There's my thinking process, guys. Multiply the numerator, multiply by 1. When I multiply everything by sine, I distribute this in. All of those inner denominators are going to cancel out. So that I'm left with cosine alpha minus 1 over cosine alpha plus 1. Now, that does not match this. I've simplified it. Making something more complex can be really hard. So what we're going to do is we're going to say, okay, I don't really know where to go from here to get this. So we're going to start here. Notice that none of these are squared functions. This has a square function. Oh, look at that. That is going to be a perfect square trinomial. Perfect square trinomials factor out to give me common factors. And this minus sine square alpha, I can use a Pythagorean identity for that. All right, so there's a starting place. So let's factor my numerator. I've got 1 minus 1 minus cosine alpha. All right, and then my denominator, if I do cosine square alpha plus sine square alpha equals 1, that's my Pythagorean identity. If I subtract this so that it becomes negative sine square alpha, that is equal to cosine square alpha minus 1, which is difference of squares, and that difference of squares will factor. So let's leave my numerator alone, because see, I've got this 1 minus cosine alpha. I need to keep one of those there. I assume I'm going to need to cancel the other one out. If I factor this, my denominator, I get cosine alpha minus 1, cosine alpha plus 1. Those do not exactly match. I've got opposites though. You know what? I've got this in the denominator. This needs to turn around in my numerator. And this I can't cancel with it like it is. So what if I factor a negative out of this in my numerator? If I factor a negative out of this binomial, it's going to match this and I can cancel it. So let's do that. Let's do a negative times cosine alpha minus 1. I factored that negative out. So then I've got 1 minus cosine alpha here, and I've got cosine alpha minus 1 times cosine alpha plus 1. Now, this cancels right there. That cancels out. If I distribute this negative back inside, if I take that negative, distribute it into this binomial, then I have cosine alpha minus 1, because that becomes a negative 1 and a positive cosine alpha, and my denominator is cosine alpha plus 1, and look at that, my sides match. I simplified both sides to a common expression. I did not work back and forth. I worked each side independently until I made my expressions match. There are other ways to get there. You know what? I'm going to show you this work. I'm not going to work through it. If you want to explore it, you can, because you can pause the video. That's an alternate approach to the same identity that we just had. Okay. Now, last identity for this section. Again, we're going to work both sides independently to simplify. I'm going to take the same approach that I did on the previous identity. I'm going to start over here on the left, and I'm going to rewrite in terms of sine and cosine. I'm going to start over here on the right, and I'm going to factor and replace until I get to a common expression. So I'm going to work through this silently. You guys work through it, pause your video, come back to see if yours matches mine. to stop there, move over to the other side and see what I can do with it. When I'm adding, life is a little easier because order does not matter. These worked out nicely because I didn't need to rearrange anything. And I simplified to a common expression. Okay. Last example for 5.2, calculator math. We're applying Pythagorean identity to electronics. Remember that trig is one of our most applicable mathematics. Take a second to read the problem talking about FM radio stations. The total energy of a circuit is given to us. E of t is equal to L of t plus C of t, and we need to simplify that based on the values that we were given. Notice that the argument is the same for both of those. I've got 5 cosine square of this amount and 5 sine square of this amount. I'm gonna simplify my life a little bit just by representing that argument with alpha because it's the same. So E of t is equal to 5 cosine square alpha, because that's this that I was given, L of t, plus C of t, which is 5 sine square alpha. And look at that, I've got a common factor of 5. I can factor out that common factor. And cosine square alpha plus sine square alpha is my Pythagorean identity. So the total energy in that circuit is 5. Whatever our, it doesn't give us a unit, does it? Okay, very good, guys. I'll see you for 5.3.